Professor Stephen Hawking and other scientists believe that to secure the future of the human species, we must colonize another planet.
We can, and must, use our curiosity and intelligence to look to the stars. We must do it now before humanity is overtaken by some disaster that we can neither anticipate nor control.
The Solar System, a cosmic expanse of celestial bodies bound by the Sun's immense gravity, represents a fascinating mixture of complexity and simplicity. It begins with the Sun at its center, a main sequence star that has been burning for approximately 4.6 billion years, and extends outward to include planets, moons, asteroids, comets, and interstellar boundaries defined by the heliosphere. The heliosphere acts as a protective bubble, shielding the solar system from galactic cosmic radiation and interstellar winds. However, this boundary is not static, as it shifts depending on the Sun's activity cycle, which lasts about 11 years. Our journey to understand the solar system's boundaries and what lies beyond has been driven by curiosity and a desire to uncover the origins of life and the universe. Since ancient times, humanity has been fascinated by the night sky, initially believing the stars and planets were gods or celestial omens. With the advent of telescopes in the 17th century, astronomers like Galileo Galilei and Johannes Kepler began to unravel the true nature of the solar system. Kepler's laws of planetary motion, published between 1609 and 1619, revolutionized our understanding of how planets orbit the Sun, paving the way for later explorations. In modern times, significant technological advancements have enabled us to push the boundaries of exploration. Missions such as the Voyager probes, launched in 1977, provided humanity with its first glimpses of the outer planets and beyond. Voyager 1 officially crossed the heliopause, the boundary of the heliosphere, in August 2012, becoming the first human-made object to enter interstellar space. Meanwhile, Voyager 2, traveling in a different direction, reached this milestone in November 2018, giving us crucial insights into the solar system's outermost regions and the interstellar medium. One of the most ambitious recent missions is the Parker Solar Probe, launched by NASA on August 12, 2018, specifically designed to study the Sun and its environment. Named after astrophysicist Eugene Parker, who proposed the existence of the solar wind in 1958, the Parker Solar Probe has made unprecedented advancements in our understanding of the Sun's outer atmosphere, the corona. In November 2021, the spacecraft made history by becoming the first human-made object to touch the Sun, coming within just 13 million kilometers of its surface. The Parker Solar Probe has revealed surprising details about the corona, which reaches temperatures exceeding 1 million Kelvin, far hotter than the Sun's surface, which averages around 5,800 Kelvin. This paradox has baffled scientists for decades, as the laws of thermodynamics suggest the outer layers should be cooler. Data collected by the probe hints at several possible explanations, including magnetic reconnection and plasma waves, which may transfer energy from the Sun's interior to its outer atmosphere. Beyond the Sun, the solar system's composition is dominated by its mass distribution. The Sun accounts for 99.86% of the total mass, with the remaining 0.14% spread across the planets, moons, asteroids, and comets. This mass dominance underscores the Sun's gravitational influence, which governs the orbits of all celestial bodies within the system. The Sun itself is composed primarily of hydrogen, approximately 74%, and helium, about 24%, with trace amounts of heavier elements like carbon, oxygen, and iron. These elements were forged in earlier generations of stars, whose violent deaths in supernovae scattered these materials across space, eventually coalescing to form the solar system. The Sun, classified as a G2V star within the stellar classification system, is a middle-aged, medium-sized star. The classification G2 refers to its surface temperature, which is around 5,800 Kelvin, about 5,527 degrees Celsius, placing it in the yellow dwarf category. The V indicates that it is a main sequence star, meaning it is in the stable phase of its life cycle, where it is primarily fusing hydrogen into helium in its core. This fusion process releases enormous amounts of energy that power the Sun, providing light and heat to the solar system. The core of the Sun is an incredibly hot and dense environment, with temperatures reaching around 15 million Kelvin, approximately 14.9 million. In this extreme environment, hydrogen atoms undergo nuclear fusion, a process where hydrogen nuclei combine to form helium, releasing energy in the form of light and heat. This fusion process generates the energy that sustains the Sun, and through a phenomenon known as Einstein's mass-energy equivalence, E equals mc squared, a small amount of mass is converted into energy. Every second, the Sun converts about 4.26 million tons of mass into energy. This energy is then radiated outward, traveling through space as electromagnetic radiation. It reaches Earth as sunlight, providing the warmth and energy essential for life on our planet. Even though the Sun contains 99.86% of the mass in the solar system, the energy produced by its nuclear fusion is a tiny fraction of its total mass, yet it is enough to power the Sun's radiation for billions of years. Despite the Sun's vast size and relatively stable nature, it is far from being a static, unchanging entity. The Sun undergoes dynamic phenomena that can have significant effects on the solar system, including solar flares, sunspots, and coronal mass ejections, CMEs. These events are manifestations of the Sun's active magnetic field and are often tied to the 11-year solar cycle, during which the activity of the Sun increases and decreases, causing variations in the number of sunspots and the intensity of solar flares. Sunspots are dark patches on the Sun's surface that occur because the temperature in these areas is lower than in the surrounding regions. They are caused by magnetic activity that inhibits the flow of heat from the Sun's interior to the surface. Sunspots typically appear in groups and are often the sites where solar flares originate. These spots are most numerous during solar maximum, which marks the peak of the Sun's activity cycle. The Sun's magnetic field becomes more tangled, and sunspot activity increases, leading to a rise in solar radiation output. These sunspots can affect Earth's space weather, influencing the performance of satellites and communication systems. Solar flares, which are powerful bursts of radiation, often accompany sunspot activity. These flares release vast amounts of energy, including X-rays and ultraviolet radiation, which can interfere with communication systems and disrupt the functioning of satellites orbiting Earth. These flares can also affect the ionosphere, leading to communication blackouts and GPS system errors. The solar wind, a continuous stream of charged particles emanating from the Sun, can also be intensified during periods of high sunspot activity. Coronal mass ejections, CMEs, are another form of solar activity that can have significant effects on Earth's environment. CMEs are massive releases of solar wind and magnetic fields from the Sun's corona, which is the outermost layer of its atmosphere. These eruptions carry large amounts of charged particles into space, and when directed towards Earth, they interact with the Earth's magnetic field. If the CME is intense enough, it can trigger geomagnetic storms, which disrupt Earth's magnetic field. These storms can cause problems with satellite communications, navigation systems, and power grids. The particles from the CME can induce electrical currents in power lines, leading to power outages, especially in regions closer to the poles. Astronauts in space are also at risk from CMEs, as the high levels of radiation can be dangerous in the absence of Earth's protective atmosphere. Despite the challenges posed by solar activity, the Sun remains the cornerstone of life on Earth. Its relatively stable nature, compared to more volatile stars, ensures that the conditions necessary for life on Earth are maintained. However, the Sun's dynamic processes can have profound consequences for space-based technologies, and understanding these processes is essential for protecting our technological infrastructure. As we continue to explore the Sun and its influence on the solar system, it becomes increasingly clear how important it is to monitor and study solar activity. Solar phenomena like sunspots, solar flares, and CMEs are not only fascinating to scientists, but they also pose practical challenges to our growing dependence on space-based technologies. With continued research, we can better predict solar activity and mitigate the risks associated with these dynamic events. The concept of the solar system's boundaries also includes the Kuiper Belt and the Oort cloud, regions populated by icy bodies and comets. The Kuiper Belt, extending from 30 to 55 astronomical units, AU, from the Sun, contains dwarf planets like Pluto, Eris, and Haumea. Beyond this lies the hypothesized Oort cloud, a vast, spherical shell of icy objects located between 2,000 and 100,000 astronomical units from the Sun, which marks the edge of the Sun's gravitational influence. While no spacecraft has yet reached the Oort cloud, its existence is inferred from the behavior of long-period comets, which originate from these distant regions. Our understanding of the solar system's boundary has evolved significantly, from early observations with rudimentary telescopes to sophisticated missions like the Parker Solar Probe and Voyager. Each step has expanded our knowledge, revealing not only the intricate dynamics of our local cosmic neighborhood but also its connection to the broader universe. As we continue to push the limits of exploration, the mysteries of what lies beyond the solar system promise to inspire and challenge humanity for generations to come. The Sun, the nearest star to Earth, is both the heart of our solar system and an enduring scientific enigma. As a G2V main sequence star, it has fascinated humanity for millennia, serving as a critical source of light, heat, and energy essential for life on Earth. Modern science, leveraging advancements in technology and space exploration, has deepened our understanding of this celestial powerhouse, yet many of its secrets remain unsolved. Central to the ongoing investigation of the Sun are its structural complexities, the phenomena driving its solar winds and magnetic fields, and the perplexing paradoxes related to its atmospheric temperatures. At its core, the Sun is a nuclear furnace where thermonuclear fusion occurs, converting hydrogen into helium at temperatures of approximately 15 million Kelvin. This process releases vast amounts of energy, which slowly radiates outward, powering the Sun's luminosity. The Sun's core constitutes roughly 25% of its radius and is the site of immense pressure, over 250 billion times the atmospheric pressure on Earth, and a density that compresses matter into plasma. Every second, about 4.26 million tons of the Sun's mass are converted into energy, which eventually escapes as light and heat. Beyond the core lies the radiation zone, spanning 70% of the Sun's radius. In this dense region, energy is transferred primarily through radiation, with photons being absorbed and re-emitted by particles countless times in a process that can take thousands to hundreds of thousands of years for a single photon to escape. The outer boundary of this zone transitions into the convection zone, where energy transfer occurs via convective currents. Here, hot plasma rises toward the surface, cools and sinks back down, creating massive vortices. These convective movements play a vital role in generating the Sun's magnetic field through a dynamo effect. The photosphere, the lowest visible layer of the Sun's atmosphere, is the source of most of the sunlight we see. At an average temperature of 5,800 Kelvin, it features sunspots, cooler, darker regions caused by concentrated magnetic activity. Sunspots were first observed by Galileo Galilei in the early 17th century, marking the dawn of solar physics. Above the photosphere lies the chromosphere, a layer that glows faintly red due to the emission of hydrogen alpha light and reaches temperatures of 20,000 Kelvin in some regions. Further out, the corona extends millions of kilometers into space and exhibits temperatures exceeding 1 million Kelvin, a fact that contradicts the expectation of a cooler outer atmosphere, a phenomenon known as the coronal heating problem. The Parker Solar Probe, launched by NASA on August 12, 2018, has revolutionized our understanding of these solar mysteries. Designed to withstand temperatures of up to 1,370 degrees Celsius, the probe has ventured closer to the Sun than any previous spacecraft, skimming through the corona to gather unprecedented data. In December 2021, it made history by becoming the first human-made object to touch the Sun. One of its primary objectives is to investigate the origin and behavior of the solar wind, a stream of charged particles emanating from the Sun at speeds of 400 to 800 kilometers per second. The solar wind, first theorized by astrophysicist Eugene Parker in 1958, profoundly influences space weather and planetary environments. It originates from coronal holes, regions where the Sun's magnetic field opens outward, allowing plasma to escape. The Parker Solar Probe has detected structures within the solar wind known as switchbacks, sudden reversals in the magnetic field direction that may hold clues about the wind's acceleration mechanisms. These findings suggest that magnetic reconnection, a process where magnetic field lines break and reform, could be responsible for energizing and propelling the solar wind. The Sun's magnetic field, generated by the dynamo effect in its convection zone, exhibits a complex, dynamic behavior characterized by an 11-year solar cycle. During this cycle, the Sun transitions between solar minimum and solar maximum, with the latter marked by increased sunspot activity, solar flares, and coronal mass ejections, CMEs. Solar flares, sudden bursts of electromagnetic radiation, and CMEs, massive expulsions of plasma and magnetic fields, can have significant impacts on Earth, disrupting satellite communications, power grids, and even posing risks to astronauts in space. In 1989, a powerful solar storm caused a 9-hour blackout in Quebec, Canada, illustrating the tangible effects of space weather driven by solar activity. Despite the wealth of knowledge gathered, the Sun continues to challenge our understanding with its coronal heating paradox. The corona's temperature, exceeding 1 million Kelvin, contrasts sharply with the photosphere's relatively cooler temperature of 5,800 Kelvin, defying conventional thermodynamic expectations. Several hypotheses have been proposed to explain this anomaly. One involves Alfvén waves, oscillations in the plasma driven by the Sun's magnetic field, which could transfer energy from the lower atmosphere to the corona. Another theory suggests that nanoflares, tiny, ubiquitous bursts of magnetic energy, might cumulatively heat the corona. The Parker Solar Probe and other missions like Solar Orbiter, launched by the European Space Agency, ESA, in 2020, aim to test these theories by providing high-resolution data on magnetic and plasma dynamics. The Sun's mysteries extend beyond its immediate vicinity. The heliosphere, a vast bubble of solar wind and magnetic field, defines the boundary between the solar system and interstellar space. This boundary, known as the heliopause, marks the point where the solar wind's pressure is balanced by the interstellar medium. Voyager 1 and Voyager 2, launched in 1977, crossed the heliopause in 2012 and 2018, respectively, offering the first direct measurements of this enigmatic frontier. The Sun's influence also shapes the habitability of planets within the solar system. Its stable output of energy, coupled with Earth's position within the habitable zone, has enabled life to flourish. However, the Sun will not remain stable forever. In approximately 5 billion years, it will exhaust its hydrogen fuel and transition into a red giant, engulfing the inner planets and potentially ending life on Earth. Understanding the Sun's life cycle is crucial not only for predicting its future but also for studying similar stars in the galaxy, many of which host exoplanets that may harbor life. The Sun is a dynamic and complex entity that remains central to our understanding of astrophysics and planetary science. From the intricate layers of its structure to the powerful forces driving its magnetic fields and solar winds, the Sun offers a wealth of scientific challenges and opportunities. Missions like the Parker Solar Probe and Solar Orbiter, complemented by ground-based observatories and theoretical modeling, continue to unveil the secrets of our nearest star. As we delve deeper into its mysteries, the insights gained will not only enhance our comprehension of the Sun, but also provide critical knowledge for exploring other stars and planetary systems in the universe. Mercury, the smallest planet in our solar system and the one closest to the Sun, is a world of extremes. Its unique geological features, fascinating history, and close proximity to the Sun make it a challenging yet intriguing subject of study. Despite being difficult to observe due to its proximity to the Sun, technological advancements have provided significant insights into Mercury's structure, surface, and composition. This chapter delves into Mercury's classification, its extraordinary geological features such as Caloris Planitia and Pantheon Fossae, and the key findings from historic space missions like Mariner 10 and Messenger. Mercury is the smallest of the 8 recognized planets in the solar system, with a radius of approximately 2,440 kilometers, making it slightly larger than Earth's moon. Its mass is 3.33 times 10 squared cubed kilograms, about 5.5% that of Earth. Despite its diminutive size, Mercury is one of the densest planets in the solar system, with an average density of 5.43 grams per cubic centimeter, comparable to Earth's. This density is largely due to Mercury's massive metallic core, which constitutes about 85% of the planet's radius. This core is thought to be primarily composed of iron and nickel, making it disproportionately large relative to the planet's size, a characteristic that continues to puzzle scientists. Mercury's large core has led to various hypotheses about its formation. One theory suggests that the planet originally had a thicker mantle, which was stripped away by a massive impact early in the solar system's history. Another theory posits that the intense solar winds near the young Sun might have blown away lighter materials during Mercury's formation, leaving behind a planet dominated by heavier elements. Regardless of its origins, Mercury's core plays a critical role in the planet's unique characteristics, including its magnetic field. Unlike Venus or Mars, Mercury has a global magnetic field, albeit one that is significantly weaker than Earth's, only about 1% as strong. This magnetic field is likely generated by a dynamo effect in its partially molten outer core, making Mercury one of the few terrestrial planets with an active magnetic field. The field interacts with the solar wind to create a magnetosphere, albeit one that is much smaller and more dynamic than Earth's, providing a protective buffer against the Sun's radiation. Mercury's surface, heavily cratered and resembling the Moon, tells a story of a geologically inactive world for the past 3.8 billion years. The absence of significant tectonic activity suggests that Mercury's crust has been stable for most of its history. However, this does not mean that the planet is devoid of fascinating geological features. Among Mercury's most notable landmarks is Caloris Planitia, one of the largest impact basins in the solar system. Caloris Planitia, Latin for plains of heat, is a massive basin with a diameter of approximately 1,550 kilometers. It was formed around 3.9 billion years ago by the impact of a large asteroid or comet. The immense energy of the impact likely melted the surrounding crust, leading to the formation of smooth plains filled with solidified lava. The basin is surrounded by a ring of mountains, some rising up to 2 kilometers high, and contains radial and concentric ridges. Interestingly, the impact that created Caloris Planitia had effects on the opposite side of the planet, creating a chaotic terrain known as the weird terrain due to seismic waves converging and disrupting the surface. In the center of Caloris Planitia lies another extraordinary feature, Pantheon Fossae, also known as the spider. This unique structure consists of over 230 radiating troughs or globins extending outward from a central point. The troughs vary in length from a few kilometers to several hundred kilometers. Pantheon Fossae's origin remains a topic of debate among scientists, with hypotheses ranging from volcanic activity to tectonic forces caused by the cooling and contraction of Mercury's crust. Mercury's geological history is further highlighted by its extensive network of lobate scarps, or cliffs, which are evidence of the planet shrinking over time. These scarps, some of which are hundreds of kilometers long and several kilometers high, are believed to have formed as Mercury's core cooled and contracted, causing the crust to buckle. This planetary contraction has reduced Mercury's diameter by an estimated 7 kilometers over its lifetime. The exploration of Mercury began in earnest with the Mariner 10 mission, launched by NASA on November 3, 1973. This was the first spacecraft to visit Mercury, and it provided humanity with its first close-up images of the planet's surface. Mariner 10 conducted 3 flybys of Mercury between 1974 and 1975, during which it mapped about 45% of the planet's surface, measured its magnetic field, and studied its tenuous exosphere. The images revealed a heavily cratered world with stark contrasts between light and dark regions, similar to the Moon. One of Mariner 10's most significant discoveries were the detection of Mercury's thin exosphere, which is composed primarily of oxygen, sodium, hydrogen, helium, and potassium. Unlike Earth's atmosphere, Mercury's exosphere is not stable but constantly replenished by processes such as solar wind sputtering, micrometeoroid impacts, and the outgassing of volatile materials from the surface. The exosphere is so thin that it is more akin to a vacuum, making Mercury highly susceptible to space weather and solar radiation. Following Mariner 10, it would take more than 3 decades before another spacecraft visited Mercury. The Messenger mission, Mercury Surface, Space Environment, Geochemistry, and Ranging, launched on August 3, 2004, was a groundbreaking endeavor that orbited Mercury from 2011 to 2015. During its mission, Messenger mapped 100% of Mercury's surface in high resolution, providing unprecedented detail about its geology, composition, and magnetic field. Messenger's discoveries transformed our understanding of Mercury. For instance, the mission confirmed the presence of water ice in permanently shadowed craters near the poles. Despite Mercury's scorching surface temperatures, which can exceed 430 degrees Celsius during the day, some craters at the poles never receive sunlight due to the planet's negligible axial tilt of 0.034 degrees. In these frigid environments, temperatures can drop below -180 degrees Celsius, allowing water ice to persist. This ice is likely mixed with organic materials, hinting at the delivery of volatile compounds by comets and asteroids. Messenger also revealed that Mercury's surface is rich in sulfur, a surprising finding that suggests the planet formed under conditions different from those of the other terrestrial planets. The spacecraft detected evidence of ancient volcanic activity, with vast plains of solidified lava indicating that Mercury was once geologically active. Additionally, Messenger's instruments identified hollows, small, irregular depressions that appear to be unique to Mercury. These hollows are thought to form when volatile materials in the crust sublimate, leaving behind voids that collapse. Another intriguing discovery by Messenger was the confirmation of Mercury's ongoing contraction. By analyzing the distribution and orientation of lobate scarps, scientists estimated that the planet's radius has decreased by up to 7 kilometers since its formation. This contraction is driven by the cooling of Mercury's interior, which continues to release heat despite the planet's small size. The success of the Messenger mission has paved the way for future exploration. The Bepi-Colombo mission, a joint project of the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, was launched on October 20, 2018, and is currently en route to Mercury. Consisting of 2 orbiters, the Mercury Planetary Orbiter, MPO, and the Mercury Magnetospheric Orbiter, MMO, Bepi-Colombo aims to build on Messenger's findings by providing even more detailed data about Mercury's surface, magnetic field, and exosphere. The mission is expected to arrive at Mercury in 2025, heralding a new era of discovery for the solar system's smallest planet. Mercury is a planet of contrasts and mysteries. Its small size belies its fascinating geology, from the vast expanse of Caloris Planitia to the enigmatic Pantheon Fossae and the towering lobate scarps. The planet's massive core, magnetic field, and volatile rich surface challenge our understanding of planetary formation and evolution. Space missions like Mariner 10, Messenger, and the upcoming Bepi Colombo continue to unlock Mercury's secrets, offering insights not only into this enigmatic world but also into the broader processes that shaped our solar system. As exploration advances, Mercury's story is far from complete, promising more revelations in the years to come. Venus, often called Earth's twin because of its similar size and composition, is a world of extraordinary contrasts. Despite its resemblance to Earth, Venus is a planet of extremes: a dense, toxic atmosphere, scorching surface temperatures, and an unparalleled array of geological features. As the second planet from the Sun, Venus lies 0.72 astronomical units, AU, away, completing its orbit in approximately 225 Earth days. The planet has fascinated scientists and astronomers for centuries, with a rich history of exploration and discovery. Understanding Venus involves unraveling its dense atmosphere, examining its geological activity and terrain formations, and analyzing data from significant space missions such as Magellan and the Soviet Venera program. Venus's most striking feature is its dense atmosphere, which is composed predominantly of carbon dioxide, 96.5%, with traces of nitrogen, 3.5%, and other gases, including sulfur dioxide. The thick atmosphere creates a runaway greenhouse effect, trapping heat and leading to surface temperatures that average around 737 Kelvin, 464 degrees Celsius, hot enough to melt lead. This makes Venus the hottest planet in the solar system, even hotter than Mercury, despite being farther from the Sun. The atmospheric pressure on Venus is about 93 times that of Earth, equivalent to the pressure found 1 kilometer beneath Earth's oceans. Venus's atmosphere is layered with thick clouds of sulfuric acid, reflecting about 75% of the sunlight that reaches the planet. This high albedo makes Venus one of the brightest objects in the night sky, often referred to as the evening star or morning star. The clouds obscure the planet's surface from direct observation, making radar mapping essential for studying its geology. Beneath the cloud layer, the atmosphere remains hostile, with winds reaching speeds of 360 km per hour in the upper layers, a phenomenon known as superrotation. However, at the surface, wind speeds are much slower, barely strong enough to move small particles of dust. Venus's surface is dominated by volcanic and tectonic activity, making it one of the most geologically dynamic planets in the solar system. It is estimated that 80% of the surface is covered by basaltic plains, formed by ancient lava flows. These plains are punctuated by thousands of volcanoes, ranging from small shield volcanoes to massive structures such as Mount Mons, which rises 8 kilometers above the surrounding terrain. While direct evidence of ongoing volcanic activity has yet to be observed, data from missions such as Magellan and Venus Express suggest that Venus may still be volcanically active. Observations of transient hotspots and changes in atmospheric sulfur dioxide levels indicate that eruptions might have occurred within the last few million years. Distinct terrain formations set Venus apart from other planets. Among these are tesserae, highly deformed regions of intersecting ridges and valleys that resemble a patchwork of tiles. Tesserae are considered some of the oldest features on Venus, potentially predating the surrounding plains. These regions are thought to have formed through a combination of tectonic and volcanic processes, reflecting the planet's complex geological history. Another unique feature of Venus's terrain is the presence of arachnoids and coronae, which are circular or oval-shaped structures often surrounded by concentric fractures. Arachnoids, so named because they resemble spider webs, are thought to form when rising magma creates stress patterns in the crust without leading to a full volcanic eruption. Coronae, on the other hand, are larger and more prominent features associated with upwelling mantle plumes. These structures provide critical clues about Venus's internal dynamics and the absence of plate tectonics. Unlike Earth, Venus lacks active plate tectonics, a feature that plays a crucial role in shaping our planet's surface and recycling its crust. Instead, Venus's lithosphere appears to be a single, stagnant shell. This leads to a different style of geological activity, where heat builds up beneath the surface until it is released in catastrophic resurfacing events. These events, which may occur every 500 million years, could explain the relatively young age of Venus's surface, estimated at about 300 to 700 million years. Exploration of Venus began in earnest during the 1960s and 1970s with the Soviet Union's Venera program, which achieved a series of historic milestones. In 1970, Venera 7 became the first spacecraft to successfully transmit data from the surface of another planet, enduring the harsh conditions for 23 minutes. Subsequent missions, such as Venera 9 and 10 in 1975, provided the first images of Venus's surface, revealing a rocky, barren landscape covered with angular rocks and fine-grained soil. Later missions, including Venera 13 and 14, were equipped with more advanced instruments, capturing color images and analyzing the chemical composition of the surface, which was found to be similar to basaltic rocks on Earth. In the 1990s, NASA's Magellan mission revolutionized our understanding of Venus by using radar mapping to produce the first high-resolution images of the planet's surface. Launched in 1989 and operational until 1994, Magellan mapped 98% of Venus's surface, revealing intricate details of its volcanic and tectonic features. The mission confirmed the dominance of volcanic plains and identified over 1,000 craters, most of which are remarkably well preserved due to the planet's lack of weathering processes. Magellan also discovered the extensive network of lava channels, including Baltes Vallis, the longest known channel in the solar system, stretching over 7,000 kilometers. Magellan's data also provided insights into the composition and structure of Venus's crust. The radar images revealed regions with varying radar reflectivity, suggesting differences in surface roughness and material properties. High reflectivity areas, often associated with tesserae, are thought to consist of ancient, highly deformed rocks. These findings have led to new theories about Venus's geological evolution, including the possibility that it once had oceans and a more Earth-like climate before experiencing a runaway greenhouse effect. The exploration of Venus has continued into the 21st century with missions such as the European Space Agency's Venus Express and Japan's Akatsuki probe. Venus Express, operational from 2006 to 2014, focused on the planet's atmosphere and climate, revealing the presence of a double atmospheric vortex at the poles and measuring variations in sulfur dioxide levels. These findings suggest the possibility of ongoing volcanic activity and highlight the dynamic nature of Venus's atmosphere. Japan's Akatsuki, also known as the Venus Climate Orbiter, entered Venus's orbit in 2015 after an initial failure to achieve orbit in 2010. The mission is primarily studying the planet's atmospheric dynamics and cloud structure, using infrared imaging to penetrate the thick cloud layers. Akatsuki's observations have provided valuable data on the superrotation of Venus's atmosphere and the distribution of heat across the planet. Future missions to Venus aim to address some of the lingering questions about its geological activity, climate history, and potential habitability in the past. NASA's Da Vinci Plus and Veritas missions, scheduled for launch in the late 2020s, will conduct detailed analyses of Venus's atmosphere and surface, respectively. Da Vinci Plus will deploy a descent probe to study the atmospheric composition and structure, while Veritas will use radar mapping to produce high-resolution images and topographical maps. These missions are expected to provide critical data on Venus's tectonic processes, volcanic activity, and the role of water in its history. In addition to these planned missions, private organizations and international collaborations are exploring concepts for human exploration and potential long-term study of Venus. The idea of aerostat habitats floating in Venus's upper atmosphere, where temperatures and pressures are more Earth-like, has been proposed as a way to overcome the challenges posed by the planet's harsh surface conditions. While still in the conceptual stage, such projects highlight the growing interest in Venus as a target for exploration. Venus remains one of the most enigmatic planets in the solar system, offering a wealth of scientific opportunities and challenges. Its dense atmosphere, unique geological features, and extreme environmental conditions make it a natural laboratory for studying planetary evolution and climate dynamics. As new missions and technologies advance our understanding of this shrouded world, Venus may one day reveal its secrets, shedding light on the processes that shape rocky planets and their potential for habitability. Mars, often called the Red Planet, has captured the imagination of humanity for centuries. Its reddish appearance, caused by iron oxide, rust, on its surface, has made it a prominent feature in the night sky and a source of myth, speculation, and scientific study. Today, Mars is one of the most explored planets beyond Earth, with missions constantly striving to uncover its secrets. Mars presents an intriguing dichotomy, a barren, frozen desert that once had conditions conducive to liquid water, and possibly even life. Central to its allure are its colossal volcanic features, like Olympus Mons and the Tharsis region, its Grand Canyon system Valles Marineris, and the ongoing efforts of robotic explorers like Perseverance and Ingenuity. Mars is a rocky terrestrial planet that is about 6,779 kilometers in diameter, making it roughly half the size of Earth. Despite its smaller size, Mars boasts some of the most massive and striking geological features in the solar system. Among them, Olympus Mons, the largest volcano in the solar system, stands as a testament to Mars's geologically active past. This shield volcano, located in the Tharsis region, rises an astounding 26 kilometers above the Martian surface, nearly 3 times the height of Mount Everest. Its base spans a staggering 600 kilometers, making it comparable in size to countries like France or Poland. Olympus Mons' immense size is largely due to Mars's lack of tectonic plate movement. Unlike Earth, where tectonic plates shift over stationary volcanic hotspots, Mars's stationary crust allows magma to erupt repeatedly at the same location. Over time, this has resulted in the accumulation of vast layers of solidified lava. Scientists estimate that Olympus Mons last erupted around 25 million years ago, relatively recent in geological terms, suggesting that Mars could still have some residual volcanic activity beneath its surface. The Tharsis region, where Olympus Mons is located, is a volcanic plateau covering about 25% of Mars's surface. The area contains several other massive volcanoes, including Ariza Mons, Pavonis Mons, and Ascraeus Mons, each rising over 14 kilometers above the surrounding plains. This region is a focal point for Mars's geological history, as the intense volcanic activity likely influenced the planet's climate by releasing vast amounts of gases, including water vapor and carbon dioxide, into the atmosphere. The volcanic bulge of Tharsis also played a significant role in the formation of Valles Marineris, a canyon system so massive it dwarfs any terrestrial counterpart. Valles Marineris, named after NASA's Mariner 9 spacecraft, which discovered it in 1971, stretches for approximately 4,500 kilometers, nearly the width of the continental United States. The canyon system plunges to depths of up to 7 kilometers and spans widths of 200 kilometers in some places, making it the largest canyon in the solar system. The formation of Valles Marineris is believed to be linked to the volcanic activity in the Tharsis region. As the region swelled due to magma upwelling, the surrounding crust stretched and fractured, creating a network of interconnected canyons. Valles Marineris provides critical evidence of Mars's past, particularly its relationship with water. The canyon walls reveal stratified layers of sediment, suggesting that water once flowed or pooled within these regions. Ancient river channels and mineral deposits, including sulfates and clays, found in and around the canyon indicate the presence of liquid water in Mars's past. These findings bolster the theory that Mars had a much thicker atmosphere and warmer climate billions of years ago, capable of supporting stable bodies of liquid water on its surface. Mars's past water activity is further evidenced by the presence of valley networks, outflow channels, and paleolakes scattered across its surface. The planet's northern hemisphere is dominated by smooth plains that may once have been the floor of an ancient ocean. If true, this ocean could have covered 20% of Mars's surface and persisted for millions of years, creating conditions potentially favorable for life. The question of whether life ever existed on Mars remains one of the central goals of ongoing exploration. Since the 1976 Viking missions, robotic explorers have been scouring the planet for signs of past or present life. The current generation of Mars missions, spearheaded by NASA's Perseverance rover and Ingenuity helicopter, represents a new frontier in this quest. Launched on July 30, 2020, Perseverance landed in Jezero crater on February 18, 2021, a site carefully chosen for its potential to preserve biosignatures. Jezero crater, with a diameter of about 49 kilometers, was once home to a large lake fed by an ancient river. The delta deposits within the crater are rich in clay minerals, known to trap and preserve organic molecules. Perseverance is equipped with cutting-edge instruments, including the Sherlock spectrometer and the Pixel instrument, to analyze rock samples for signs of ancient microbial life. The rover's drill is capable of extracting core samples, which will eventually be stored for retrieval by a future mission as part of the Mars Sample Return Program, a collaborative effort between NASA and the European Space Agency, ESA. Perseverance is also studying the Martian environment to prepare for future human exploration. It carries the MOXIE experiment, designed to produce oxygen from Mars's carbon dioxide-rich atmosphere. This technology could pave the way for sustainable human missions by providing breathable air and fuel for rockets. Additionally, the rover is equipped with weather sensors and cameras to document dust storms and other atmospheric phenomena that could affect human operations. Accompanying Perseverance is Ingenuity, the first powered aircraft to fly on another planet. This small, lightweight helicopter has demonstrated the feasibility of aerial exploration on Mars, achieving its first flight on April 19, 2021. Ingenuity's success opens new possibilities for planetary exploration, allowing scientists to scout inaccessible terrains and identify potential sites of interest for future missions. Its flights over Jezero crater have already provided high-resolution images that complement Perseverance's ground-based observations. Beyond NASA's missions, international efforts are expanding our understanding of Mars. The ExoMars program, a joint venture between ESA and Roscosmos, aims to search for biosignatures and study the planet's subsurface. The Rosalind Franklin rover, part of this program, is equipped with a drill capable of reaching depths of 2 meters, where ancient organic materials may be better preserved from radiation. The HOPE probe, launched by the United Arab Emirates in 2020, is studying Mars's atmosphere and climate, focusing on seasonal changes and the behavior of dust storms. Mars exploration has also benefited from orbital missions, which provide a global perspective on the planet's features and processes. NASA's Mars Reconnaissance Orbiter, MRO, has been mapping the surface in incredible detail since 2006, identifying sites of interest for rovers and revealing changes in surface features over time. Similarly, ESA's Mars Express, operational since 2003, has contributed valuable data on the planet's geology and potential water reservoirs. The search for water and signs of life on Mars is not just about understanding the planet's history, it also has implications for human exploration. Water is a critical resource for future crewed missions, both for life support and as a component of rocket fuel. Evidence of subsurface ice, detected by radar instruments aboard Mars Express and MRO, suggests that water is more abundant than previously thought. These reservoirs could serve as a vital resource for astronauts living and working on Mars. Mars also presents numerous challenges for human exploration. Its thin atmosphere, composed mainly of carbon dioxide, offers little protection from cosmic radiation and ultraviolet light. Dust storms, which can cover the entire planet for weeks, pose risks to equipment and solar-powered systems. Despite these obstacles, organizations like NASA and SpaceX are actively developing technologies to enable human missions to Mars within the next 2 decades. As we continue to explore Mars, each mission builds on the discoveries of its predecessors, painting an increasingly detailed picture of the red planet. From the towering peaks of Olympus Mons to the winding depths of Valles Marineris, and from ancient riverbeds to the dusty plains of Jezero Crater, Mars offers a glimpse into a world that was once active and potentially habitable. The insights gained from studying Mars not only expand our understanding of the solar system, but also bring us closer to answering one of humanity's most profound questions: are we alone in the universe? The asteroid belt is a vast region in our solar system that lies between the orbits of Mars and Jupiter, stretching from approximately 2.1 to 3.3 astronomical units, AU, from the Sun. This zone is populated by countless small celestial bodies, primarily composed of rock and metal, that vary greatly in size and composition. Though collectively these objects contain only about 4% of the mass of the Moon, the asteroid belt remains a significant area of interest for scientists seeking to understand the formation of our solar system and the processes that shaped the planets. The asteroid belt's composition is diverse, with the objects ranging from tiny grains of dust to massive bodies several hundred kilometers across. The largest asteroid, Ceres, is large enough to be classified as a dwarf planet due to its size and spherical shape, measuring about 940 kilometers in diameter. Vesta, another prominent object, is the second largest body in the asteroid belt and a major subject of study. While these objects are relatively small compared to the planets, they provide critical insights into the early solar system, as they are considered remnants from its formation. The composition of asteroids in the belt varies depending on their location and classification. There are 3 main types of asteroids: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic. C-type asteroids, which make up approximately 75% of the known asteroids, are rich in carbon and water, and are thought to be some of the oldest objects in the solar system. These asteroids are typically dark and reflect little light. S-type asteroids are composed primarily of silicate minerals like olivine and pyroxene, and they are generally brighter than C-types. M-type asteroids, though less common, are made largely of metals, especially iron and nickel, and can have significant amounts of iron-rich material. Ceres, located in the asteroid belt, is of particular interest because it is the only object in the belt classified as a dwarf planet. It is composed mostly of water ice, rock, and salt, making it a unique object in the solar system. Ceres has been the focus of exploration by the Dawn spacecraft, which arrived in 2015 after spending nearly a year orbiting the asteroid Vesta. Ceres's surface features suggest it may have had an ocean of liquid water beneath its icy shell in the distant past. These findings have sparked interest in the possibility of microbial life existing on Ceres, as liquid water is considered a key ingredient for life as we know it. Vesta, another key member of the asteroid belt, has a diameter of about 525 kilometers, and is one of the largest and brightest objects in the belt. Unlike Ceres, Vesta is primarily composed of rock and metal, with a differentiated structure, including a core, mantle, and crust. Its surface is heavily cratered, with a particularly notable impact crater, Rhea Silvia, which is one of the largest and most well-preserved craters in the solar system. The surface features of Vesta suggest it has a more active history than many of its neighbors, and it is thought to have experienced significant differentiation early in its formation. Theories regarding the origin of the asteroid belt have evolved over time. One of the most widely accepted hypotheses is that the asteroid belt represents the remnants of a planet that never formed. Early in the history of the solar system, there was sufficient material in this region to form a planet. However, the gravitational influence of Jupiter, the largest planet in the solar system, is thought to have prevented this material from coalescing into a planet. Jupiter's immense gravity caused the protoplanetary material in the belt to undergo frequent collisions, preventing the formation of a single large body. Instead, these objects remained as individual asteroids, orbiting the Sun in a relatively stable configuration. Jupiter's gravitational influence not only prevented the formation of a planet but also shaped the structure of the asteroid belt itself. Kirkwood gaps, regions where there are fewer asteroids, are thought to have been created by the gravitational interactions between Jupiter and the objects in the belt. These gaps occur at specific distances from the Sun, where the gravitational pull of Jupiter destabilizes the orbits of asteroids, pushing them out of the region or causing them to collide with each other. The existence of these gaps provides strong evidence of Jupiter's influence on the asteroid belt and its role in shaping the dynamics of the solar system. The asteroid belt is also thought to be the source of many near-Earth objects, NEOs, which include asteroids and comets that occasionally pass close to Earth's orbit. Some of these objects may have originated in the asteroid belt but were displaced by gravitational interactions with Jupiter or the planets, causing them to cross Earth's orbit. Understanding the composition and structure of the asteroid belt is crucial for identifying potential hazards from NEOs and developing strategies for planetary defense. The exploration of the asteroid belt began in the 20th century with telescopic observations, but it was not until space probes were sent to the belt that detailed data became available. The most significant missions to the asteroid belt have been NASA's Dawn spacecraft and ESA's Hera mission, both of which provided valuable insights into the composition and history of the belt's largest objects. The Dawn spacecraft, launched in 2007, spent nearly 8 years studying two of the largest bodies in the belt, Vesta and Ceres. Dawn's mission was groundbreaking because it was the first to orbit and study two different extraterrestrial bodies, giving scientists a rare opportunity to compare and contrast two distinct types of objects from the asteroid belt. Dawn's first target was Vesta, which it orbited from 2011 to 2012. During this time, the spacecraft mapped the surface of Vesta in high resolution, discovering a wealth of information about its surface composition, cratering, and geological history. One of the most important findings was evidence of water-rich minerals on the surface, suggesting that Vesta may have undergone a period of water-related activity. The spacecraft also observed that Vesta had been heavily impacted by asteroids, with craters and ridges indicating significant tectonic processes in its past. After completing its study of Vesta, Dawn traveled to Ceres, arriving in March 2015. Ceres is much smaller than Vesta, with a diameter of about 940 kilometers, and it is made primarily of ice and rock. Dawn's observations of Ceres revealed several intriguing features, including bright spots in the Akata crater. These bright spots were later identified as deposits of sodium carbonate, a type of salt. The discovery of these salts, along with the detection of organic compounds, led scientists to hypothesize that Ceres may have had an underground ocean in the past and could potentially harbor microbial life. Dawn's mission concluded in 2018, but its legacy continues to shape our understanding of the asteroid belt. The data collected by the spacecraft has provided crucial information about the history of the solar system, the processes that shaped the formation of the planets, and the potential for life beyond Earth. In addition to Dawn, other space missions have contributed to our understanding of the asteroid belt and its inhabitants. The NEOWISE mission, which uses infrared observations to detect and characterize near-Earth objects, has provided valuable data on the composition of asteroids and comets. NASA's OSIRIS-REx mission, which launched in 2016, aims to collect samples from the asteroid Bennu, a near-Earth object that is thought to have originated in the asteroid belt. OSIRIS-REx's sample return mission, expected to return samples to Earth in 2023, will provide scientists with direct evidence of the composition and structure of an asteroid from the belt, offering valuable clues about the early solar system. Looking ahead, the HERA mission, a joint effort by the European Space Agency, ESA, and NASA, aims to study the binary asteroid system of Didymos and its moonlet, Didymoon. This mission, set to launch in 2024, will provide additional data on asteroid dynamics and could help prepare for future asteroid deflection techniques. The focus on binary asteroids is significant, because these systems offer insight into the processes that govern asteroid formation and evolution, providing a better understanding of the asteroid belt as a whole. The asteroid belt, despite its sparse distribution of objects, is an area rich with scientific significance. The asteroids within the belt are remnants from the early solar system and preserve information about the conditions that existed in the protoplanetary disk from which the planets formed. They are time capsules, preserving clues about the materials and processes that shaped the solar system billions of years ago. As we continue to explore the belt with new missions and advanced technologies, we will undoubtedly unlock more secrets about the formation of the solar system, and the role of small bodies in planetary evolution. The asteroid belt is a region of incredible scientific interest. From the massive objects like Ceres and Vesta to the smaller, more numerous asteroids, the belt offers insights into the early solar system and the forces that shaped the planets. Theories about its origin, particularly the role of Jupiter in preventing the formation of a planet, have been supported by observations of the belt's structure and the presence of gaps caused by Jupiter's gravitational influence. Space missions like Dawn and OSIRIS-REx have revolutionized our understanding of the asteroid belt, revealing important details about its composition and history. As exploration of this region continues, we can expect to uncover even more revelations about the building blocks of our solar system. Jupiter, the largest planet in the solar system, is a giant gas planet that is surrounded by dozens of moons, each with its own unique features and mysteries. Among these moons, Ganymede, Callisto, and Europa stand out as prime candidates in the search for life beyond Earth. While none of these moons currently support life as we know it, they each exhibit characteristics that suggest they might harbor conditions conducive to life. The discovery of subsurface oceans, magnetic fields, and active geysers on these moons has made them central to modern astrobiology and planetary science. This chapter will explore the potential for life on these three fascinating moons, focusing on the scientific findings and hypotheses regarding their environments. Ganymede, the largest moon of Jupiter and the largest natural satellite in the solar system, is a fascinating world that has long intrigued scientists. With a diameter of about 5,268 kilometers, Ganymede is even larger than the planet Mercury. Ganymede's composition is similar to that of the rocky planets, consisting of a mixture of water ice and silicate rock. It is the only moon in the solar system known to have a magnetic field, making it a unique object of study. Ganymede's magnetic field was first detected by NASA's Galileo spacecraft in the 1990s. It is believed to be generated by an internal dynamo, similar to Earth's, where the moon's liquid iron nickel core generates a magnetic field. This is significant because most moons in the solar system, including others orbiting Jupiter, do not have their own magnetic fields. Ganymede's field is much weaker than Earth's, but it still creates a complex interaction with Jupiter's powerful magnetosphere, forming a magnetosphere around the moon. This interaction produces auroras at Ganymede's poles, much like the northern and southern lights on Earth. What makes Ganymede even more interesting is the evidence suggesting the presence of a subsurface ocean beneath its icy crust. Data collected by the Galileo spacecraft, Hubble Space Telescope, and more recently, NASA's Juno spacecraft, has shown that Ganymede has a layered structure with a water ice crust, a silicate mantle, and an iron-nickel core. Underneath the ice, scientists believe there could be a global subsurface ocean of liquid water. This hypothesis is based on evidence of gravitational anomalies observed by Galileo, which suggests the moon's ice is floating on a liquid layer. In addition to the gravitational data, scientists have detected patterns in Ganymede's magnetic field that suggest the presence of a conducting liquid layer beneath its icy surface. The Juno mission, which arrived at Jupiter in 2016, has helped refine these models of Ganymede's magnetic field, providing further evidence that there is likely an ocean beneath the moon's thick icy shell. This ocean could be located about 150 kilometers beneath the surface, and if it exists, it would be the largest subsurface ocean discovered outside of Earth. The possibility of a subsurface ocean on Ganymede raises the question of whether this moon could harbor life. While the conditions on Ganymede are far from hospitable by Earth standards, the presence of water and the possibility of hydrothermal activity on the ocean floor offer the potential for chemistry that could lead to life. On Earth, life thrives around deep-sea hydrothermal vents, where superheated water rich in minerals provides the necessary conditions for life to flourish in the absence of sunlight. A similar environment on Ganymede's ocean floor could theoretically support microbial life. However, there are challenges to this hypothesis. The icy crust of Ganymede is thick and cold, with surface temperatures averaging around 100 Kelvin, about -173 degrees Celsius, which makes it difficult for liquid water to exist at the surface. The ocean beneath the crust, however, could be kept warm by tidal heating generated by Ganymede's gravitational interactions with Jupiter and its neighboring moons, Io and Europa. This tidal heating, along with the potential for chemical reactions in the ocean, could create a habitable environment for life, though any life would have to be extremophilic, adapted to survive in harsh, cold, and dark conditions. Another of Jupiter's moons that has garnered significant scientific attention is Callisto, the second largest of Jupiter's moons, with a diameter of about 4,820 kilometers. Callisto is often considered a frozen relic of the early solar system, as its surface is one of the oldest and most heavily cratered in the solar system. Unlike Ganymede, Callisto does not appear to have a magnetic field, but it is believed to have a differentiated interior, with a core, a mantle, and a surface layer rich in water ice. Callisto's surface is covered with a thick layer of ice, which is thought to be up to 150 kilometers thick. Below this icy crust, scientists hypothesize that there could be a subsurface ocean that remains liquid due to the same tidal heating mechanisms that are thought to affect Ganymede. Callisto's interactions with Jupiter's immense gravitational field and the other moons may generate just enough heat to keep the ocean beneath its icy crust from freezing solid. This subsurface ocean would likely be located around 100 kilometers beneath the surface. Unlike Ganymede, Callisto does not appear to experience significant tidal forces due to its orbital configuration. This suggests that if there is a subsurface ocean, it would likely be more isolated from Jupiter's magnetic field and from the other moons' gravitational influences. This isolation could make Callisto's ocean an interesting target for study, as it may have developed under different conditions than those on Ganymede or Europa. The potential for life on Callisto is speculative, but the existence of a subsurface ocean beneath the icy crust would make it a candidate for further exploration. If the ocean is indeed present, the conditions beneath Callisto's surface could be stable over long periods of time. Like Ganymede, the ocean could be kept warm by tidal heating or by radioactive decay in the moon's interior. If these conditions exist, it is possible that microbial life could be supported in the ocean, though it is likely to be limited to extremophilic organisms capable of surviving in the cold, dark depths. NASA's Juno spacecraft, which has been studying Jupiter and its moons, has also provided valuable data about Callisto. Although Juno's main mission is to study Jupiter's atmosphere and magnetosphere, it has gathered important information about Callisto's surface and interior. Future missions, such as the Europa Clipper mission, which is scheduled to launch in 2024, may include flybys of Callisto to further investigate its potential for a subsurface ocean, and to assess its suitability as a target for future astrobiology research. Of all of Jupiter's moons, Europa has garnered the most attention from the scientific community in the search for extraterrestrial life. Europa is slightly smaller than Earth's moon, with a diameter of about 3,100 kilometers, but it has one of the smoothest surfaces in the solar system, with only a few large craters. The surface of Europa is made primarily of water ice, and it is believed to conceal a vast, liquid water ocean beneath. This ocean could harbor the necessary conditions for life, making Europa one of the most promising targets for astrobiological exploration. Europa's most striking feature is its icy surface, which is divided into large plates of ice that have been moved around by tectonic activity. These ice plates appear to have been broken apart and rotated, suggesting that the moon's ice is floating on a subsurface ocean. The interaction between the surface ice and the ocean beneath is thought to play a key role in shaping Europa's geological features, including the large fractures and ridges that crisscross its surface. In addition to its icy surface, Europa is unique in that it exhibits signs of geological activity in the form of geysers. In 2001, the Hubble Space Telescope detected plumes of water vapor erupting from Europa's south pole, indicating that the subsurface ocean is in contact with the surface and that there may be active interactions between the two. These geysers appear to be spouting water and ice from beneath Europa's icy crust, suggesting that the ocean is not entirely isolated from the surface. The discovery of these plumes has fueled excitement in the search for life, as the plumes may provide a way for scientists to sample Europa's ocean without having to drill through the thick ice. The presence of a subsurface ocean on Europa has significant implications for the potential habitability of the Moon. Europa's ocean is thought to be in contact with the Moon's rocky mantle, and the possibility of hydrothermal vents on the ocean floor provides a potential source of energy for life. On Earth, life exists around hydrothermal vents deep in the ocean, where hot, mineral-rich water supports ecosystems independent of sunlight. If Europa's ocean has similar conditions, it could support microbial life, potentially even forms of life that are radically different from anything we know on Earth. Europa has been studied extensively by NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, providing valuable data about Europa's surface and magnetic field. The upcoming Europa Clipper mission, set to launch in 2024, will conduct detailed studies of Europa's surface, ocean, and geysers, with the goal of determining whether the Moon has the necessary conditions to support life. The mission will conduct flybys of Europa and use a suite of scientific instruments to study the ice, the subsurface ocean, and the Moon's potential for habitability. The moons of Jupiter, Ganymede, Callisto, and Europa, each offer unique and compelling reasons for exploration, especially in the search for extraterrestrial life. Ganymede's magnetic field and subsurface ocean, Callisto's icy surface and potential ocean, and Europa's active geysers and subsurface ocean all suggest that these moons could harbor the conditions necessary for life. While life has not yet been discovered on any of these moons, the evidence of water and the potential for hydrothermal activity provides hope that life, even in microbial form, may exist beyond Earth. As missions like Europa Clipper, Juno, and future probes continue to explore these moons, we may one day answer the question of whether we are truly alone in the universe. Saturn, the second largest planet in our solar system, is a celestial giant known for its stunning system of rings, which has captivated astronomers and the public alike for centuries. The planet itself is composed mainly of hydrogen and helium, with a relatively small rocky core surrounded by a deep atmosphere, but it is its extensive ring system, and the diverse array of moons orbiting it that truly makes Saturn a unique and fascinating object of study. Saturn's rings are not just beautiful, they are complex and dynamic, revealing insights into the processes that govern planetary formation, the interactions between moons and their environments, and the nature of the solar system's outer reaches. To fully understand the science behind Saturn's rings and moons, we need to explore their composition, formation theories, interactions, and the missions that have enhanced our knowledge of this incredible system. The composition of Saturn's rings is diverse and is one of the key factors that makes them so intriguing. The rings themselves are made primarily of countless individual particles, ranging in size from tiny grains of dust to chunks that can be up to several meters across. These particles are composed mostly of water ice, with varying amounts of rock and dust mixed in. The ice in the rings is highly reflective, which is why Saturn's rings appear so bright and dazzling when observed from space or Earth. The amount of rock and dust mixed with the ice decreases with the distance from Saturn, with the innermost rings being composed primarily of darker material, possibly containing more silicate dust and organic compounds. The outermost rings, on the other hand, tend to be purer ice. The ice in Saturn's rings is believed to be relatively young, with a composition that may be similar to the original material that formed the outer planets billions of years ago. However, the exact ages of the rings are still a matter of debate, with some scientists suggesting they could be as young as 100 million years, while others propose they could be as old as Saturn itself. The rings of Saturn are divided into several distinct sections, with the most prominent being the A, B, and C rings. The A ring is the outermost of the three major rings and is separated from the B ring by a gap known as the Cassini division, a dark region that was discovered by the astronomer Giovanni Domenico Cassini in 1675. The B ring, which is the brightest and most massive of Saturn's rings, is located just inside the Cassini division, and the C ring is the innermost major ring. In addition to these primary rings, Saturn's ring system contains several fainter rings and gaps, including the D ring, the E ring, the F ring, and the G ring. These rings vary in density and structure, and their composition can change depending on their proximity to Saturn. The formation of Saturn's rings is still not entirely understood, but there are several leading theories. One possibility is that the rings are remnants of a moon or moons that were torn apart by Saturn's strong tidal forces. According to this theory, a moon or a group of moons once existed within the Roche limit, the region within which the tidal forces from Saturn would exceed the moon's self-gravity, causing it to disintegrate. This process, known as tidal disruption, could have occurred relatively recently in the history of the solar system, and the debris from the destroyed moons could have formed the rings we see today. The Roche limit is located about 2.44 times the planet's radius from Saturn's center, and any moon within this region would be susceptible to being broken apart by the planet's gravity. Another theory suggests that Saturn's rings could be the remnants of material that never coalesced into a moon due to the gravitational influence of Saturn itself, or that the material was captured from the surrounding space environment. According to this hypothesis, the rings could be composed of the remnants of a primordial disk of material that existed around Saturn when the planet was forming. This disk might have contained the building blocks of moons, but the gravitational forces at work in the region may have caused the material to spread out into a flat ring system instead of coalescing into larger bodies. The idea that the rings could be as old as Saturn itself is supported by observations of the chemical composition of the rings, which suggest that the ice in the rings contains relatively little contamination from the surrounding space environment, indicating that it has been relatively isolated for a long time. The interactions between Saturn's moons and its rings are another fascinating aspect of the Saturnian system. Saturn's moons exert a significant influence on the rings, both by shepherding material within the rings and by affecting the structure of the rings themselves. Some moons, known as shepherd moons, help to maintain the boundaries of the rings and confine material within specific regions. These moons have a gravitational influence that can prevent ring material from spreading out or escaping. One of the most famous shepherd moons is Pandora, which orbits just outside the A ring and helps to maintain the sharp edge of the ring. Similarly, the moon Prometheus orbits just inside the F ring and helps to confine its material. In addition to shepherding material, the moons also contribute to the complex structure of Saturn's rings. For example, the gravity of certain moons can create waves and oscillations within the rings, which are seen as undulations or ripples in the ring material. These gravitational interactions can cause the rings to become tightly packed in some regions and more diffuse in others. In some cases, moons can also create gaps in the rings, such as the Cassini division, which was likely formed by the gravitational interactions between the moon Mimas and the B ring. The moon's gravitational interactions with the rings also contribute to the formation of ringlets and other structures within the rings. These interactions are highly dynamic and continue to shape the rings over time. The interactions between the moons and the rings are not limited to gravitational forces alone. Some of Saturn's moons, particularly Enceladus and Titan, have been found to interact with the rings through the emission of particles. Enceladus, one of Saturn's icy moons, is known to have geysers that spew water vapor and ice particles into space, and some of these particles are believed to contribute to the material found in Saturn's E-ring. The E-ring is a faint ring that lies outside the more prominent A, B, and C rings and is thought to be composed of particles from Enceladus's plumes. Similarly, Titan, Saturn's largest moon, emits a constant stream of particles into space, which could also contribute to the ring system in ways that are still not fully understood. The study of Saturn's rings and moons has been greatly advanced by a series of space missions, most notably NASA's Cassini-Huygens mission. Launched in 1997, Cassini entered Saturn's orbit in 2004 and spent nearly 13 years studying the planet, its rings and its moons. The Cassini spacecraft provided unprecedented close-up images of the rings, revealing the complex structure of the rings and the ways in which the moons influence their formation. Cassini also observed the interaction between Saturn's moons and the rings in greater detail than ever before, providing data on how the moons contribute to the waves, gaps, and overall structure of the rings. In addition to its observations of the rings, Cassini made groundbreaking discoveries about Saturn's moons. For example, the spacecraft provided evidence of subsurface oceans on moons like Enceladus and Titan, revealing that these moons may harbor environments that could support life. In 2017, Cassini completed its mission with a dramatic series of orbits that took it through the gap between Saturn's atmosphere and its innermost ring, before it was deliberately plunged into the planet to ensure that it did not contaminate any of Saturn's moons. The data gathered by Cassini continues to shape our understanding of Saturn's rings and moons, and future missions are poised to build upon these discoveries. One of the most exciting future missions is the Dragonfly mission, which is scheduled to launch in 2027. Dragonfly will be a rotorcraft that will explore Titan, Saturn's largest moon. This mission will examine Titan's atmosphere, surface, and potential for life, with a particular focus on the moon's organic chemistry and the possibility of prebiotic chemistry. While Dragonfly will not directly study Saturn's rings, it will contribute to our understanding of Titan's role in the broader Saturnian system. In addition to Dragonfly, scientists continue to explore ways to study Saturn's rings in more detail. New technologies and techniques, such as high-resolution imaging, are helping to reveal the intricate dynamics of the rings and their interactions with the moons. These ongoing studies will likely provide new insights into the formation and evolution of Saturn's rings, as well as the broader processes that shape planetary ring systems in general. Saturn's rings and moons are among the most fascinating and dynamic systems in the solar system. The composition of the rings, the various theories about their formation, and the ways in which the moons interact with them provide key insights into the processes that shape planetary systems. The Cassini mission, along with future missions like Dragonfly, will continue to deepen our understanding of these remarkable features, potentially unlocking new secrets about the early solar system, the potential for life in the outer solar system, and the broader dynamics of planetary formation and evolution. The outermost regions of our solar system, beyond the orbits of the 8 recognized planets, are two enigmatic and largely unexplored zones that hold the key to understanding the origins and evolution of the solar system. These regions, known as the Kuiper Belt and the Oort cloud, contain ancient remnants from the early solar system. These objects, primarily composed of ice and dust, represent the building blocks that formed the planets, moons, and other bodies within the solar system. Together, the Kuiper Belt and the Oort cloud play a crucial role in understanding the solar system's formation and dynamics. The Kuiper Belt, located just beyond the orbit of Neptune, has gained increasing attention over the last few decades due to its rich diversity of icy objects and its potential role as the origin of short-period comets. Beyond the Kuiper Belt lies the Oort cloud, a massive, spherical region that is thought to be a source of long-period comets. These distant, icy realms have only been studied indirectly until recently, but with the advent of missions like New Horizons, our understanding of these far-off regions has expanded dramatically. Both the Kuiper Belt and the Oort cloud continue to intrigue astronomers and planetary scientists as they offer glimpses into the early solar system's history, the dynamics of icy bodies, and the potential for finding other planetary systems in the galaxy. The Kuiper Belt is a region of space located beyond the orbit of Neptune and extending out to about 50 astronomical units, AU, from the Sun. It is populated by a vast number of small icy bodies, including dwarf planets, comets, and other frozen objects. The Kuiper Belt is often compared to the asteroid belt that lies between Mars and Jupiter, but the Kuiper Belt is far larger and more expansive, containing objects that are much colder and more distant. The Kuiper Belt's primary significance lies in its role as a remnant of the early solar system. It is believed to contain the leftover building blocks of the solar system's formation, providing a record of the conditions that existed during the solar system's early history, more than 4.5 billion years ago. The Kuiper Belt contains objects that are relatively unchanged since the formation of the solar system, preserving information about the processes that led to the formation of the planets. These objects are thought to be composed mostly of ice, rock, and dust, materials that were left over after the formation of the giant planets like Jupiter and Saturn. One of the key features of the Kuiper Belt is the presence of dwarf planets, including Pluto, Haumea, Makemake, and Eris. These objects are similar to planets but do not meet all the criteria for planetary status. Pluto, in particular, was once considered the 9th planet in our solar system, but in 2006, it was reclassified as a dwarf planet by the International Astronomical Union, IAU. Despite its reclassification, Pluto remains one of the most studied objects in the Kuiper Belt due to its size, composition, and interesting features. The Kuiper Belt is also the source of short-period comets, which are comets that take less than 200 years to complete one orbit around the Sun. These comets are thought to originate from the outer regions of the Kuiper Belt, and their periodic nature makes them more predictable and easier to observe than the long-period comets that come from the Oort cloud. Short-period comets have highly elliptical orbits, and their orbits can be influenced by the gravitational pull of the giant planets, particularly Jupiter. The study of these comets provides valuable information about the early solar system's composition and the dynamics of the outer solar system. In addition to short-period comets, the Kuiper Belt is thought to be home to a variety of smaller objects known as trans-Neptunian objects, TNOs. These objects, which include asteroids, comets, and other icy bodies, are found in the region beyond Neptune, and many of them are thought to be in stable orbits that have not been significantly disturbed by gravitational interactions with the giant planets. Some of these objects are thought to be remnants of the early solar system, while others may have been captured or influenced by the gravitational pull of Neptune and the other outer planets. The Kuiper Belt is also important because it provides a window into the outer regions of our solar system. While the inner solar system has been extensively studied by space probes like Voyager 1, Voyager 2, and Parker Solar Probe, the Kuiper Belt remains largely unexplored. However, the New Horizons mission, which made a historic flyby of Pluto in 2015, provided the first detailed images of a Kuiper Belt object. This mission revolutionized our understanding of the Kuiper Belt by revealing the detailed surface features of Pluto and its moons, as well as providing important data about the composition and structure of the Kuiper Belt itself. The Oort cloud is a vast, hypothetical region that lies far beyond the Kuiper Belt, extending from about 2,000 astronomical units to potentially as far as 100,000 astronomical units from the Sun. Unlike the Kuiper Belt, the Oort cloud has not been directly observed, and its existence is still theoretical. However, the Oort cloud is thought to be the source of long-period comets, which have highly elliptical orbits and take thousands of years to complete one orbit around the Sun. The Oort cloud is believed to be a spherical shell of icy objects that are scattered throughout the outer reaches of the solar system. These objects are thought to be remnants from the early solar system, possibly formed during the same time as the Kuiper Belt objects. The Oort cloud is thought to be a region of space that contains a vast number of cometary nuclei, small icy bodies that are made of frozen gases, dust, and organic compounds. While comets from the Oort cloud are rarely observed, they are important because they provide valuable insights into the early solar system and its chemical composition. Comets that originate from the Oort cloud are known for their long, highly elliptical orbits, which bring them close to the Sun and then take them far out into the solar system. These comets are typically composed of a mixture of water ice, carbon dioxide, and other volatile compounds, which sublimate, turn from solid to gas, as the comet gets closer to the Sun. This sublimation creates the comet's distinctive tail, which is made of gas and dust particles that are blown away from the comet by the solar wind. One of the most famous long-period comets to come from the Oort cloud is Comet Hale-Bopp, which was visible from Earth in 1997. This comet had an orbital period of about 2,500 years and was one of the brightest comets to be observed in modern times. While most Oort cloud comets have much longer periods, the study of long-period comets like Hale-Bopp provides scientists with important information about the composition of the outer solar system and the processes that shaped the solar system's formation. The existence of the Oort cloud is inferred from the behavior of long-period comets, which have orbits that suggest they come from a distant, spherical region of the solar system. These comets often exhibit irregular trajectories, which suggests they are influenced by the gravitational forces of distant stars, other galaxies, or the overall mass distribution in the Milky Way. In addition to their influence on the orbits of comets, the Oort cloud is thought to have been influenced by the gravitational interactions of nearby stars and the galactic tide, which could have caused objects to be scattered out into the far reaches of the solar system. The Oort cloud is also thought to be the source of distant comets that occasionally pass through the inner solar system, such as Comet Eson and Comet Neowise. These comets, though relatively rare, offer valuable insights into the chemical makeup of the outer solar system, and the processes that may have shaped the formation of the solar system's planets and moons. The exploration of the Kuiper Belt and Oort cloud has been limited due to their vast distances from Earth and the challenges involved in reaching such far-off regions. However, missions like New Horizons and upcoming spacecraft are helping to expand our knowledge of these distant regions. Launched in 2006, New Horizons was the first mission to explore the Kuiper Belt in detail. The spacecraft made its historic flyby of Pluto in 2015, providing the first close-up images of Pluto and its moons, as well as gathering important data about the composition and structure of the Kuiper Belt. After its flyby of Pluto, New Horizons continued its journey into the Kuiper Belt, where it made a flyby of Arrokoth, formerly known as Ultima Thule, in 2019. Arrokoth, a small Kuiper Belt object, provided scientists with the first direct observations of a body from the outermost reaches of the solar system, offering critical insights into the early solar system, and the processes that led to the formation of the planets. In addition to New Horizons, future missions are planned to explore the Kuiper Belt and beyond. For example, NASA's James Webb Space Telescope, JWST, set to launch in 2021, will be able to study the outer solar system, including the Kuiper Belt and distant objects in the Oort cloud. JWST's advanced infrared capabilities will allow scientists to observe these regions in unprecedented detail, revealing new information about the composition and structure of these distant bodies. The Kuiper Belt and the Oort cloud are two of the most fascinating and mysterious regions of the solar system. The Kuiper Belt is home to a wealth of icy bodies and dwarf planets, while the Oort cloud is thought to be the source of long-period comets. Together, these regions offer vital clues to the early solar system's formation, the dynamics of icy bodies, and the potential for life beyond Earth. As missions like New Horizons continue to explore these distant frontiers, we are gaining a deeper understanding of our solar system's origins and the processes that shape planetary systems throughout the galaxy. The dream of traveling beyond our solar system has captivated humanity for centuries, evoking thoughts of distant stars, otherworldly life, and the boundless mysteries of the cosmos. As our technological capabilities evolve and our understanding of space deepens, the prospect of interstellar travel, moving beyond the confines of our Sun's influence into the vast expanse of the Milky Way galaxy, has become more plausible. This chapter explores the technologies and missions that are pushing the boundaries of space exploration, delving into the search for exoplanets, signs of extraterrestrial life, and the profound philosophical and scientific implications of exploring the universe. Interstellar travel is an enormous challenge, one that requires innovations far beyond what current space exploration technologies allow. At present, the fastest spacecraft humanity has ever built, NASA's Parker Solar Probe, travels at a speed of 700,000 km per hour, which is fast by human standards but still far too slow to reach even the closest star systems within a human lifetime. To reach interstellar distances, new technologies are being developed that aim to make the dream of traveling beyond our solar system a reality. One of the most discussed concepts for interstellar travel is the Breakthrough Starshot initiative, launched in 2016. This mission is part of the Breakthrough Initiatives, a group of projects aimed at exploring outer space, and its goal is to send tiny, lightweight spacecraft to the closest star system, Alpha Centauri, within 20 years of launch. The concept behind Breakthrough Starshot involves the use of light sails, which are thin, reflective surfaces pushed by powerful laser beams. These laser-powered sails would theoretically accelerate small probes to speeds of up to 20% the speed of light, an incredible feat compared to current spacecraft velocities. Once the spacecraft reach their target, they would collect data and send it back to Earth, potentially providing humanity with the first close-up images and data from an exoplanetary system. The STARS Hot mission is still in its early stages, and there are many challenges to overcome, including developing the required laser technology, building the ultra-lightweight probes, and ensuring reliable communication over vast distances. Nonetheless, if successful, it would mark a monumental leap forward in humanity's ability to explore other star systems. Another promising concept for interstellar travel is nuclear propulsion, which could revolutionize the way we explore space. One proposed approach is nuclear fusion, the process that powers stars, including our Sun. A spacecraft using nuclear fusion would rely on the energy released from fusing hydrogen atoms into helium, potentially providing a much more efficient propulsion system than conventional chemical rockets. This technology is still in the experimental phase, with significant hurdles to overcome before it becomes a viable option for interstellar travel. An alternative concept is nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant, such as hydrogen, to extremely high temperatures before ejecting it through a nozzle to create thrust. NASA has been researching nuclear thermal propulsion for several years, and while it is not yet capable of interstellar travel, it could significantly shorten travel times to other planets in our solar system and beyond, making the journey to distant stars more achievable in the future. In addition to these propulsion systems, advanced artificial intelligence, AI, and autonomous spacecraft are likely to play a critical role in interstellar missions. Because interstellar travel would take many years or even centuries, spacecraft would need to be highly autonomous, capable of making real-time decisions without human intervention. Air could help spacecraft navigate through space, avoid obstacles, and manage resources during long-duration missions. Additionally, air could be used to analyze the vast amounts of data collected from exoplanetary systems, identifying potential signs of habitability or life. Despite these advancements, there are still many technological challenges to overcome before interstellar travel becomes a reality. The distances involved are mind-boggling. For example, the nearest star to Earth, Proxima Centauri, is located about 4.24 light-years away. With current propulsion technologies, a spacecraft would take tens of thousands of years to reach this distance. Even with more advanced technologies like those proposed in the Breakthrough Stars Hot initiative, travel to nearby stars would still take decades, requiring new methods for long-term space travel, resource management, and crewed missions. As we look to the stars, one of the primary goals of future space exploration is the search for exoplanets, planets that exist outside our solar system. In recent years, the discovery of exoplanets has become one of the most exciting frontiers in astronomy, with thousands of these distant worlds identified by telescopes like NASA's Kepler Space Telescope and Transiting Exoplanet Survey Satellite, TSS. These discoveries have expanded our understanding of the potential habitability of other planets and the conditions that might support life elsewhere in the universe. Exoplanets come in a wide variety of sizes, compositions, and orbital configurations. Some are similar in size and temperature to Earth and are located in what is known as the habitable zone, the region around a star where liquid water could exist on the planet's surface, crucial for life as we know it. These planets are often referred to as Earth-like exoplanets, and identifying them has become a primary objective for astronomers in the search for extraterrestrial life. The study of exoplanets is helping scientists refine our understanding of the factors that make a planet habitable. Factors such as the planet's size, its atmosphere, its distance from its parent star, and the presence of liquid water all play a critical role in determining whether a planet could potentially harbor life. Telescopes like the James Webb Space Telescope, JWST, which is set to launch in 2021, will allow astronomers to study exoplanets in unprecedented detail. One of JWST's key objectives will be to analyze the atmospheres of exoplanets, looking for the presence of gases like oxygen, methane, and carbon dioxide, which are often associated with biological processes on Earth. Detecting these gases in an exoplanet's atmosphere could be one of the first direct signs of extraterrestrial life. In addition to looking for Earth-like exoplanets, scientists are also searching for signs of biosignatures, indicators that life may exist or may have existed in the past. Biosignatures can take many forms, from the presence of certain chemicals in a planet's atmosphere to patterns in the planet's surface geology that suggest the past presence of liquid water. The detection of biosignatures would be a groundbreaking discovery, offering evidence that life exists elsewhere in the universe. The search for biosignatures is already underway, with missions like Mars rover Perseverance investigating signs of past microbial life on Mars, and future missions to moons like Europa and Enceladus, both of which have subsurface oceans and may harbor microbial life. In the search for extraterrestrial life, astronomers are also looking for signals from intelligent civilizations. The SETI, Search for Extraterrestrial Intelligence, program has been scanning the skies for decades, searching for radio signals or other communications that might indicate the presence of advanced civilizations on distant exoplanets. Although no definitive signals have been detected, the search continues, with new methods and technologies being developed to scan broader sections of the electromagnetic spectrum for signs of intelligent life. As humanity advances in space exploration and expands its reach beyond the solar system, the philosophical and scientific implications of these efforts become increasingly profound. One of the most significant questions raised by the exploration of the cosmos is whether we are alone in the universe. The discovery of even microbial life elsewhere would have profound implications for our understanding of biology, evolution, and the conditions necessary for life. It would challenge our place in the universe and force us to rethink our conceptions of life, consciousness, and intelligence. The search for extraterrestrial life also raises profound ethical and philosophical questions. If we were to discover life on other planets, especially intelligent life, how should we approach these civilizations? What ethical responsibilities would we have, both toward these life forms and toward our own species? The possibility of interstellar communication, and the potential for peaceful or hostile encounters with extraterrestrial civilizations, raises questions about humanity's role in a larger cosmic community. In addition to the search for life, space exploration beyond the solar system raises questions about the future of humanity. As Earth faces challenges such as climate change, overpopulation, and resource depletion, space exploration offers the possibility of securing a future for humanity beyond our home planet. The colonization of other planets, moons, or even star systems could provide humanity with new opportunities for growth, survival, and exploration. However, this raises important ethical and environmental concerns about the colonization of new worlds. What rights would humanity have to claim these planets, and what impact would our presence have on any existing ecosystems? Space exploration also forces us to confront our place in the universe. The vastness of space, the overwhelming distances between stars, and the potential for billions of other star systems in the galaxy, all of these challenge our sense of scale, our understanding of the uniqueness of Earth, and our aspirations as a species. Our desire to explore the stars reflects a deep-seated yearning for discovery, a desire to understand the unknown, and a search for meaning beyond the confines of our planet. The future of space exploration beyond the solar system is filled with immense promise, and profound challenges. Key technologies like laser-propelled light sails, nuclear propulsion, and artificial intelligence will be crucial in enabling humanity to reach the stars. Missions like Breakthrough Stars Hot and the James Webb Space Telescope are poised to open new frontiers in the search for exoplanets and signs of extraterrestrial life. The philosophical and scientific implications of exploring the universe are vast, from redefining our place in the cosmos to addressing the ethical dilemmas of encountering other life forms. The quest to explore beyond the solar system is not just about technological achievement, it is about answering humanity's deepest questions about life, the universe, and our future. As we continue to push the boundaries of space exploration, we will undoubtedly discover new worlds, new forms of life, and new perspectives on our own existence, forever changing our understanding of the universe and our place within it. We'd love to hear your thoughts in the comments below. If you enjoyed the video, don't forget to hit the like button, share it with others, and subscribe for more thrilling content. Thank you for journeying with us here on Frontiers of Infinity.